From ContainerDays Hamburg, this video is proudly presented by DuxIT.
My name is Haralambos, but you can just call me Babis for simplicity. But first of all, just a short question. How many of you have heard before about Unikernels and stuff? Okay, that's okay. Okay, so for the rest of the people, you will heard something more exotic today. Let's a bit introduce about ourselves. We are a small company. We are involved in various research and commercial projects, and also a lot of open source projects, with mainly focusing on lightweight virtualization, hypervisors, container runtimes, hardware acceleration, and lately bringing cloud-native concepts for AIDS devices. So we are in ContainerDays, so I don't have to explain what containers are, but something that maybe you have heard in the past, that we had this kind of notion that containers will replace VMs, right? And of course they did, because containers allowed us to easily package our application with all the dependencies and the configuration files in one single binary, and not a single binary, in a specific format that we could easily distribute and deploy it everywhere. That was great, but we're back to VMs, because we spawn containers inside the VMs, and there is a good reason why we do that. And that's because of the isolation of containers. Containers are just real processes in our system. They use classic process isolation mechanisms like user access control, capabilities, and stuff like that. They use kernel mechanisms like namespaces, C groups, seccomp, that restrict the view of the kernel and the rest of the system, but also maybe some kind of other modules like AppArmor and Cell Linux for better security. But at the bottom line, they all share the same kernel. And that's where things can get scary. Because as we know, containers might contain a lot of CVs. The code that we have there might not be the most perfect code. And there are also use cases that we allow people to just deploy arbitrary code in their container in our system. And we treat these cases as malicious users. And in this if these malicious users are in our system, they will try to gain access to our host. And to do that, they will try to get to escalate from the container runtime. Container runtime might contain some bugs. There are a lot of bugs, there are a lot of CVs, even in runc, containerd, in a lot of other cases, and these containers can escape. Or they can target the kernel and escape again. And if they do that, they will gain access to the whole machine, they will gain access to other containers, and at the end they will gain access to everything. So how we can make that? How can we, what we can do here is that we can sandbox the containers. And the idea here is to provide an extra level of isolation in order to not allow the container to directly communicate with the host kernel, but having an intermediate layer that will intercept anything that the container tries to do, and therefore provide an extra level of isolation. And there are mainly two mechanisms that exist out there for this purpose: software-based and hardware-assisted. That's the VM that we are talking about. In the case of software-based sandbox, the most prominent solution out there is gvisor. So gvisor is creating a container, and inside this container, instead of just spawning the application as traditional container runtimes do, it creates a sandbox where the application is running inside the sandbox. To make this a bit more clear, the sandbox, the gvisor is creating this sandbox using two components that are called sentry and gopher. So when we create a pod, for example, in Kubernetes, this pod will, instead of running the application directly inside, it will spawn sentry, which is a user space kernel that intercepts every system call that the application does, and then tries to handle it. If it is not able to handle it, it will pass it through gopher, and through gopher to the host kernel. So in that way, gvisor significantly reduces the view that the application can have to the host kernel and the interaction that it can have. In the case of hardware-based sandbox, like the traditional VMs that we know, we have kata containers. Kata containers is a container runtime that creates a virtual machine for us, and inside this virtual machine, it creates a container where the application will execute inside. Again, in a Kubernetes cluster, the kata containers will create a VM using a specific Linux kernel that they distribute, a specific rootfs which contains some specific binaries like the kata agent, And the idea here is that the kata agent communicates with the kata runtime running on the host, and they interact with each other in order for the kata runtime to instruct kata agent to create containers inside the VM. It's a gRPC communication. And that's how we spawn the containers with kata. So this creates, this of course make it quite very nice and sandbox containers, but on the same time, adding additional layers, we know that this will create, might hurt the performance. And to do that, we try to measure the boot time of this sandboxed container runtimes. So to do that, we created a simple cluster and we deployed Knative there, and we have a very simple demo application, which is a C HTTP reply. It's an HTTP server that just sends a stupid hello world. And the idea here is that we invoke it from the cluster and it will go through all the Knative stack that we see there, these lines all the way here. And what we do is that we change the runtime. So in order to evaluate, for example, kata, runc, or gvisor, we just deploy the same function with a different runtime, and we measure the same time that it takes for the request to reach all the points when we have a cold boot scenario, reach this function here, return the result to the kubeproxy, and then from kubeproxy return back to our client. Okay, so here are the results. They are disappointing. We can see that gvisor, kata, either with Firecracker or with Kemu, they can induce a 2 times overhead more than runc when we spawn a new container from the cold boot scenario. And that's quite bad. And we are greedy because we want to have the container's performance. We want to have how fast they can execute, how fast they can spawn. We want to have this kind of ease of use of the containers. We have Kubernetes, we have so many tools for containers, which are great. And that's what exactly gvisor and kata allows us to do. But on the same time, we need to have strong isolation. We want to have as much isolation as possible when we care about it, for example, in multi-tenant environments. And the thing is that right now, it's not that straightforward. So let's see how we can do that. The first thing that we look is that we have a very bloated stack. Even for just some small workloads, this is very bloated. So we have a virtual machine inside the container and time inside the container and then the application running. So let's start removing stuff. We don't need all of this. Of course, we cannot remove the VM because that's what the strongest isolation boundary we can have there. What can we reduce here? Any ideas? Okay, no one wants to participate. The container runtime. So the idea here is that we can totally get away with the container runtime inside the VM. We don't need it, and we just run the application inside the VM, and we can even modify the guest kernel to have a very specialized kernel for a specific application, and then we can just spawn a container as a VM. And that's okay. We can, it's a small optimization, but it's still good. But this is a concept of a single application kernel. Now, in the cloud native era, we know that the workloads are very specialized for a specific purpose. So, for example, a gateway doesn't require a lot of things that depend that the library, the runtime, or the guest kernel have. These components, for example, if we have a gateway, we might not need storage. So we might not even file systems or block or anything. And that's where Unikernels comes. Unikernels allows us to combine everything that an application needs in a single binary, only with the necessary components. Cherry picking only what, for example, the application needs from the language runtime, from the external libraries, or even from the guest OS. And we can this is a single binary that we can boot over a virtual machine monitor. Okay, but we also get a lot of this question of how can we build and deploy these things, because containers are the de facto application packaging technology out there right now. And we will do that, we will just build them like containers. And how we can do that? We can do that with Bunny. Bunny is a build-kit frontend, so it provides a container-like experience. It has the same exactly workflow with Docker. So the idea here is to simplify the whole process of building an application as a single application kernel or as a unikernel, and it removes all of the burden from the user to to set up the framework and get the dependencies and everything that is required, and everything is handled from the bunny. The idea is simple. As exactly with Docker, we have a specific file, bunny file in this case, which is just a YAML instead of a container file, and the user specifies that, then bunny will fetch all the building layers. It can be, depending on the workflow that we have, like a unikernel or even a single application kernel like Linux. And then inside these building layers, it will build the unikernel for us, the rootfs, and it will create a new OCI image. Now, this OCI image significantly differs from traditional OCI images because we have a kernel inside. So in the case of single application kernel, like Linux, we need to append in this OCI image one more layer that will be the Linux kernel that we will execute, that we will use to execute this container. If you have a unikernel, the green things that you see there are all combined in one single binary. So we just have, for example, in this case, only two layers, the unikernel and the configuration files or any other kind of files that the application requires. So I will show you a quick demo of how this works. So we are here, so I will go back here. I hope that's good enough. Let me show you how the bunny file looks like. So here we will build a Mirage unikernel. Maybe it's not very visible, but what I want you to notice is that we specify as a platform the Mirage unikernel. As an application, we will have here, this is an example application that Mirage uses. It's an HTTP server, and we will just simply say that we want to build this application with that name. The path is from the local build context and specifically from the current working directory. So let me try, before I do that, let me change here and remove everything. Okay, and now I will just do a simple Docker build. That's all. Now I'm gonna also post it in our harbor so we can later deploy it. And I will just do that, and this will simply fetch everything from the layers that are required in order to build Mirage OS, and it will slowly, as you can see, slowly start building everything that Mirage requires in order to build this unikernel. And as I said, this is an OCaml unikernel. So just to show you, I do not have any OCaml or anything here. So going back to the presentation, I will leave that running because it takes a lot of time. But later, hopefully, when we come back, everything will be built. Hopefully. So, okay. Let's say that we built this thing, how we can deploy it. And we know that containers are the de facto application deployment technology out there. Everything is built around containers. We have Kubernetes, we have so many tools. Everything is easy and manageable with containers. So we will do exactly the same thing again. We will just deploy them as normal containers. They will be visible as containers. But as you saw before, the OCI image significantly differs. So we need a different container runtime. The normal container runtimes do not have the information, they do not have the logic to handle, let's say, how they can deploy a unikernel, how they can spawn a VM. And that's where urunc comes. So urunc tries to be the runc for unikernels and single application kernels. It's a new CNCF sandbox project. It's a CRI-Compatible, written from scratch. Not the best idea we ever had. But since we are here, it worked. It supports both software-based and hardware-assisted sandboxes, so it can have both the same concept as Divisor, where we have a software sandbox, but also with kata containers where we use VMs, and it's highly extensible and customizable. we can simply add a new monitor, a new sandbox, a new guest without any modifications, either in the guest, either in the monitor. You can even run FreeBSD there. So to show you the key differences is that urunc, as you can see, it kind of resembles a bit what gvisors do. It creates a container, and inside this container, it creates a sandbox, which is a monitor, and then inside there we will run the application. So if we use VMs, this monitor will be a virtual machine monitor. Okay, so a bit more details. In urunc, the application is tightly coupled with the guest kernel. So if we have a Unikernel, as I said before, our application is the kernel. If we have a single application kernel, then we have one more extra layer, which is the kernel that we will use in order to boot the VM. And urunc will use this kernel to instruct the virtual machine monitor to boot this virtual machine. And it will treat the monitor. The KVM VM is just another process. So whatever we apply in a normal container, we will just apply in that process. All the namespaces, all the C groups, all the user-specific stuff, all the configuration, it will be applied in that particular process. Therefore, we treat it as the container process. And this, of course, has the limitation that we can only have one VM per container, but it has the other benefit that it allows us to have fine-grained isolation even inside the pods. So let me show you what that means. When we deploy a pod with urunc over Kubernetes, the sidecar containers, the containers that are part of the platform, part of our stack, like as a platform engineer stacks, they will be handled as traditional, normal containers. We don't need to isolate them. We trust them. We created them. On the contrary, the user container, we don't know what happens inside there, and we don't trust it. So that's what we're going to isolate. And urunc will create a necessary container for this container, and it will spawn the VM inside there. And of course, it will take care of the networking part that is required in order to have access this VM to the outside world. Okay, so let's see how this compares to the other solutions that we had. We have here, we did the exact same benchmark as before, but here we have in the middle we have Linux over Firecracker and Camel as a single application kernel, and on the rest we have some unikernels like Rampran, which is a NetBSD-based unikernel, and Unicraft, which is a new unikernel. POSIX-friendly unikernel. And as you can see with Linux, we have a less overhead, close to 30%. And with unikernels, we can even get down to 16 or even around 20% in the worst case scenario. Much better. So yeah, let's go back and see if our unikernel is built. No, it's still building. So let's continue with the rest of this. But we have more interesting demo, don't worry about that. So we have this kind of, we have created this small website that we can, that we can play. Yeah, I cannot do that. I can do it like that though. So I will go here. So this is very similar to the stack that I showed before for the evaluation. It's a Knative cluster. I can show you here that we don't have any pods running. And I will show you the services that we have. So here we have the Knative services that they're running. By the way, this one is built. So we have built it as here. This is what we have. We can do, I will try to do a copy paste here. Let me, just to show you that this is a new image, just let me push it with this kind of tag. So I will go here and I will change this one. I will just add this one so we can pull the new image, and I will deploy it. Oh yeah, but before I deploy it, let me show you that the only thing that we need to do is just specify a new runtime. That's all. We can deploy a Unikernel just specifying the runtime that we want to. And of course, urunc needs to be part of the cluster, right? We need to have urunc installed in our system. So let me apply that. Okay. And we will see that we will have some pods running. Yeah, the container is creating and it's running. So here is a name. It's called Mirage HVT. And we will go here. We have created a very dummy web page that we can allow us to invoke this application. So we will put here, oh, no, that's wrong. That's also wrong. Okay, and we will just call the function. Now, what's going to happen here is that we see that we create new pods every time that we have it. And I can, if we are lucky enough, maybe I can do a watch. Okay, so I will invoke it again, okay? And we will see new containers spawning. And yeah, here we don't see the actual thing. Maybe the watch is too slow, but because it's completely terminated, like this is scaled to 0. So as soon as the request is served, it will return. So maybe if I do a top, this will be visible. I don't know. Let me try again. So somewhere here we should see something called solo 5. Doesn't seem to be visible. That's weird. Okay. That was very fast too. How can we specify the time in watts? Someone remembers? The same, thank you. Okay, oh yeah. This one? Oops. Okay, oh yeah. So let's try again. Yeah, so we have this, you can see this is spawning a Solo 5. Solo 5 is a very, very minimal virtual machine monitor. It uses KVM, and it's very, very lightweight, specifically for Unikernels. Now, let's do something else. We have here some other images. By the way, you can access this by yourself. And we have here, for example, that you can test it out with a Hello World and even a JSON to YAML converter. So let's try this out. We will go here to post, and we will do a JSON to YAML with runc, and I will need the JSON example. Okay, so let me get this one. I will call it, and this will just return here. So we have a here we can see also the conversion, and let me just try and do here. Okay, it's a bit flunky, but let me try and do it again. Here, the request body, so we can refresh the diagram. And I will show you, for example, we can do just gvisor, and this will invoke gvisor. And in the meantime, here you can see the pods that are spawning, that they are gvisor pods, there can be runc pods. We can also do it with kata. can also do it with Firecracker. And here you can see that we have, oh yeah, here we have to do a Firecracker. You see that the Firecracker is spawned. This is with kata. Now we can do the same thing with urunc. So we can have urunc, Linux, and this will create, it will have, okay, maybe I did something wrong. Maybe I haven't deployed it. Do we have it? Okay, I did it wrong. Okay, so here we have it, and you can see that we have, oh, I was not doing a what. But you can see another process of Firecracker running here, which is the urunc process that was created. And we can do it also with Unicraft. And again, we have the same result. Here is the result, that is a conversion. So here in the times, you can see that there is some time. You can play around a lot with that. And you can get quite, you can see by yourself the execution. Like try to execute it a lot of times, try to play around with it, and you can see the difference in time in the graph. You will see that, yeah, and how this changes between the different runtimes. Okay, so I don't know if you want to play around or if you want just scan this QR code, it will get you to this website and you can paste around these kind of things and you can play around with that. Or just come by later and just let me know if you have any problems with that. Yeah, let me return to slideshow. I would like to note that this work is partially funded from European research projects. And to summarize, containers provide the ease of use and the fast spawn times that we want, and they are the de facto packaging and deployment system that we have right now. But on the same time, they don't provide strong isolation, especially for multi-tenant environments. And we are quite jealous of VMs in this kind of scenario because they are the standard, the most powerful isolation mechanism that we can have out there. But there is the existing container runtimes induce significant overhead, sandbox container runtimes, and urunc tries to find a balance between that. So we don't have this kind of huge overhead in performance when we use strong isolation boundaries, like even with virtual machines. urunc is open source. As I said before, it's a CNCF sandbox project, so please join us in the CNCF Slack workspace. You can find a channel called urunc there. And yeah, we also have a website with documentation and everything of how you can make this, try it by yourself. And that's all from my side.
The first one would be, how does urunc handle networking and storage compared to standard container runtimes?
Okay, so that's a good question. So I don't think I can share my slides again, right?
Sorry?
I cannot share my slides again, right?
Can we share the slides again?
So I will go back to this diagram. So as you can see here, when we have a normal container runtime, we have a virtual Ethernet inside the network namespace, where the container is usually, which container usually gets everything from, like from the rest of the outside world, okay? But in the case of urunc, what we do is that we have a top device that is like somehow bridged with a virtual Ethernet interface, and therefore everything is tightly connected, so whatever comes to the virtual Ethernet, it also goes to the VM. It's actually, we just stole it from Kata. Kata containers do the same thing. Regarding storage, so we are in the work in progress to provide support for volumes, but currently we don't have any, because some Unikernels don't have support for a lot of block devices. It was not our focus, but slowly we are working on that, and it will be, in the next release, we will also have support for persistent volumes.
Thank you. The next question is, are there limitations around debugging when running Unikernels with Urunc?
Yeah, so I think this question is in general with Unikernels and debugging. There are quite a lot of... so what happens with urunc is just the container runtime. So we can debug everything outside of urunc, and then we can simply deploy it with... and we can then just deploy it with urunc. So in the case of Unikernels, there has been some kind of work that people are trying to improve the debugging inside the Unikernel. And urunc can easily be extended in order to provide this kind of support. But also in the case of Linux, for example, if you just have if you have a single application kernel and you use Linux as a kernel, then you don't have anything. You can just do the same debugging that you do. Like, it's the same image. It just boots inside the VM. So it doesn't differ at all with what you would have if you run the same image, for example, in any other kind of container runtime.
Thank you. The last question seems off topic. Is OSV still a thing? I don't know what
actually, it's still maintained. And if someone is excited of OSV, we will be happy to help them add support for it in urunc. There are so many Unikernels out there, so many projects, so yeah.
Okay, then thanks for answering the questions and thanks for the amazing talk. Enjoy the evening.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.